Hello, fellow YouTubers. Allow me to introduce myself. My name is Edward, and I'm an electronics engineer. In this series of videos, I'm going to be taking you through through my Karnaugh maps research. But before I even start, I just wanted to tell you a few things. First of all, I wanted to try YouTube out. It has a lot of very interesting qualities. The most important one is it's free and available 24/7. So this in itself is interesting because it allows people to actually just look at this whenever they have the time and to look at it as many times as they need to in order to criticize, correct, apply, or whatever the contents. I like that a lot. And the second, not to mention the discussion possibilities, and the second thing I really like about this is it's international. That's why I'm doing this video in English. I'm a Mexican. I speak Spanish. And I'd like this information to be spread around in this medium and reach as much of an audience as possible, especially since this is such a very basic design tool. Now, there's another reason I'm tempted to use this rather than just go the usual publishing conference route, and this is beyond my range of. This is outside my scope. I'm usually focused into systems control. But while doing an undergraduate course, I found that this was a very limited technique and didn't like that. So I want to correct it and all, but I don't want to invest that much time into it. I don't have that many resources available at this moment. And I think this is a very good way in which I can just share this in an access basis in the hopes that you can make use of it. So without further ado, let's just step into it. First of all, what is a Karnaugh map? Well, a Karnaugh map is basically a graphical tool for solving Boolean functions. We just minimize them, actually. We don't solve them. We minimize Boolean functions with this graphical tool. And a Boolean function is a function that accepts only zeros and ones as its inputs, as its values, and that is very convenient for describing digital circuits. Okay, we won't touch all possible digital circuits. We're just going to consider combinational circuits, which are circuits that only care about what's happening in this instant rather than what happened in previous future iterations or whatever. There's no sequences, just circuits of addition, arithmetic operations, conversions, and such kind of circuits. Okay. Now, Karnaugh maps are usually restricted to 4 inputs, and in this particular video, those are the Karnaugh maps we're going to be talking about, just to make sure that we're all sharing common ground, and to help out those guys with the homeworks and problems to understand this stuff. So, okay, before I can actually tackle Karnaugh maps, I need to talk to you about a pair of things. First of all is the truth table. A truth table is basically a map of inputs to an output. Now, since most systems actually have multiple outputs, we would actually need multiple truth tables to represent them. And as for its inputs, we have 2 letters in this chart, A and B. Those are called literals, and those are the actual hardware inputs we would have in the digital circuit. We're going to use them as variables in a sense, but they're called literals, okay? And I'm going to be referring to them as such. And at the other end, right, we have f of A and B. Well, that's the output. We have some kind of series that performs, let's say, a function to those inputs and gives us an output. Okay, so let's look at a trivial example. We'll look at the OR function, one I'm sure most of you, if not all of you, are familiar with. Now, the OR function basically just says that if we get 0 on every input, we get a 0 at the output, and otherwise we just get a 1. So the second thing I need to talk to you guys about is the canonical form. The canonical form will work for us as a bridge between the truth table and Boolean algebra. That's not to say that it is. It's a way in which we represent a function using all of the minterms that are needed. And minterms are groups of literals multiplied together. Now, in order to obtain the canonical form, what we first need to do is just look at the truth table and locate ones. We have 3 ones right here. Now, to obtain the respective minterms, what we do is, well, let's just look at the first one. We have A apostrophe B. A apostrophe means not A. That is the opposite of A. Since we can only have 0 and 1, the opposite of 0 is 1. Now we have them one next to each other, which is the equivalent to multiplication, or thought as the equivalent to multiplication. I won't get into mathematical details. We'll just consider as if they were multiplying. So if we multiply the opposite of 0, that is 1, by 1, we get 1 at the output. Simple enough, huh? We multiply the opposite of 0, 0, we get a 1. Okay, so we have 1 and the opposite of 0, A not B, we get a 1 at the output. A and B, 1 times 1, we get a 1 at the output. That's it. Next, we add them up. And we say, well, if the first condition is met, or the second condition is met, or the last condition is met, we get a 1 at the output. And yes, this is the same OR we're actually trying to analyze, and we're applying it. I said it was a trivial example. Now, let's look at a Karnaugh map. Karnaugh map is a simple matrix where we're going to dump the truth table, and then we're going to manipulate it without using algebra. So, first of all, what we know is that if there's only zeros at the input, we get a 0 at the output. So there it is. And we also know that otherwise we get a 1, so we just put 1s in the rest of it. Okay, so next, we're going to need to group neighboring rows and cells. There's more to grouping, but we'll cover it in an as-needed basis. So how can we group them? Well, we can group them vertically and horizontally for now. Okay, so let's just group them horizontally. That's with the row of 1, all these ones, and vertically. So what happened? Well, first of all, we'll look at the row of 1. If A equals 1, then whether B equals 0 or B equals 1, we have a 1 at the output. But we need A to equal 1. So there's the A letter. Likewise, when B equals 1, we have a 1 at the output, whether A equals 0 or 1. Doesn't really matter what A's value is, but we need to have B as a 1. And we add these guys up, and we get A plus B, or A or B. If either A or B are 1, we get a 1 at the output, which is what this function is supposed to do. And we can now compare it to the original canonical form with 3 terms. Now we've lost a term, and our terms are simpler. So let's just go back and look at how this happened. Well, first of all, when we grouped the row of A, we eliminated a minterm. Both of these ones haven't been grouped before, so we just eliminated a minterm, and we simplified one of the terms. Every time we group an ungrouped number, we simplify. And if all of the other numbers are also ungrouped, we'll eliminate. Okay? So that's how it works. The second time, we used a one that had already been grouped, so we just simplified the other one. So that's what we have. 2 simplified minterms and instead of the 3. So there's only 2, and they're, let's just say, linear. Okay, so let's look at 3 literals. With 3 literals, we get 2 choices. We can add more rows or columns. We're adding more columns, which means we have, aesthetically, a pair of 2 input Karnaugh maps, one side by side. But what we're actually going to be doing is we're going to be adding more elements to our columns. We're going to add a C. And as for the numbers, we're going to need 2 of them, one for B and one for C. Now, the important thing is that this sequence can be any sequence you want. This is the standard sequence. But then it has to change 1 bit at a time. So we have 00 to 01. Only one of the bits changed. 01 to 11. Only one of the bits changed. Now, another thing that matters is we have 2 numbers here, or 2 bits. That means we have 2 neighbors. So 01 has the neighbor of 00 and 11. But 00 has 2 neighbors as well. That is 01 and 10. So the leftmost and rightmost column are both neighbors. We're looking at a cylinder. Okay? So let's go for it and do an example. Now, we can group the 01 column, but there's something else that's going to come into play now. We can group in powers of 2. So let's just wrap these 4 ones in just one single bundle. Now we are going to obviously discard more minterms and simplify a little bit more. The other thing we're going to be doing is we're going to just group that last one over there, and we just simplified a minterm. Couldn't discard anymore, but we already have discarded quite a few. So let's look at the answer. We have a C. So why do we have a C? Well, because we have this group of 4 ones, this 4-1 group, we have ones where A equals 0 and ones where A equals 1. So A is not affecting the output and can be discarded. Likewise, B is not affecting the output and can be discarded. The only condition we have for having a 1 at the output with all of these, that all of these have in common, is that C equals 1, and we have it there. A non-inverted C, just a normal standard C without inversion. C. Okay, likewise, for A and B, well, they're in the row of A, so A equal 1. So A has to equal 1. There's just no way around it. And in both columns, B equals 1. The only one that changes, and this is what we're going to be looking for, the only bit that toggles is C's. So bit toggles within the group, that's a literal that gets discarded. So we discard C in this one, and we discard A and B in the other one. And now we add them up, and we have A and B plus or C. So for literals, well, now we're going to add more rows, right? Yep. Now we have A and B for rows and C and D for columns. And as for the numbers, well, we're just going to take them from our columns. We're just going to repeat the same thing. Likewise, we're going to have the topmost and bottommost rows to be neighbors. So we're looking at a toroid here. Just think of it as a strange kind of donut. Okay? We're looking at a donut. I'm getting kind of hungry. Okay, so next up, an example. Okay, so you see, I'll just wait a few seconds, and time to group them. Okay, so we managed to pull off 3 groups of 4. Awesome, huh? But the important thing is we also have in the 1, 0 column, the 0, 0 column, and the 1, 0 row, sorry, the 0, 0 column and the 1, 0 column grouping sets of 1s. So there we can see what I was telling you about the cylinder and, well, basically a toroid now effect coming into play. I like to think of this as Pac-Man logic. You go out the left and you come out the right. You go out the top and you come out at the bottom, and it's a kind of strange thing. I like that. So variables are grouped by powers of 2. Extremes are considered neighbors. And this is the end of the first video. Thank you very much for your attention, support, whatever. I hope you enjoyed this, and this should help you out with your homeworks. Next ones, we're going to be looking at multiple inputs. Particularly, the next one is just going to be 5 and 6 inputs. It's going to be the standard procedure. So thank you very much for your time again, and I'll see you there.